That's good, pretty good. Okay. MKT RF minus MKT dot RF. Okay. It's MKT minus with freedom. Okay. Pretty good. Yes, nothing is significant. Okay. How about you guys?
Sure. I'm sorry. I find that regression on the internet in Korean, so I understand that. However, at first I faced the obstacle to roll the pharma three factors, but there was text file, but I failed to roll that file in R. So.
How about you? Where is your homework? Where is your homework? Give me reasonable excuse. So please send your homework to Google. Thank you. Your homework is very important for your grade. If you don't submit homework properly, you cannot expect a grade from it. And today we will have a guest speaker from 230. He is a quant in Mirae. Mirae is one of the largest asset manager in Korea. And unfortunately, he will give us Korean talk. I mean, you can leave at 2:30. Okay.
All right.
Okay, it is fine. You don't have to stay. Korean lecture. Okay. But I think it is perfect opportunity for you to know what is really going on in the field. Okay, so it was very important homework, so you have to do it again. Except you don't have to do it again.
Is it programming in R?
Yes. So, I mean, for you, since you didn't take any TA hour or anything about R, if you are familiar with any other package, statistical package, you can use that.
I will try to find one.
Okay. I mean, actually, for this regression homework, you can even do the Excel. You can even use Excel, actually. So, Sohae, how about your homework?
Oh, I mean the regression?
Yeah.
Actually, I did the regression, but there's no no Google Groups to upload, isn't it? Do I have to?
Yes. Show me your homework then. So I mean by default, please submit your homework to Google. Do you have any interview or something?
No.
Why did you dress up?
My friends
이거요. 그래. So you cannot find homework?
No, internet is not connected.
Okay, then please submit your homework to Google Group later.
Okay.
Thank you. Okay, last week we learned the basic of univariate regression. Fitting, testing, yes, we learned that. T distribution and goodness of fit, okay. And okay, goodness of fit. How well does your model fit the data? Okay, basically, goodness of fit measures that. So consider total squared error. Okay, TF is total sum of squared error. So yi is basically your data, right? Data you are predict, and y bar is your model. Okay, and then therefore, actually, you can write down. So y bar is actually average. So it is deviation, square deviation from the average. And you can decompose that as yi minus your estimate of the yi, which is yi hat, and yi hat minus average of the y. And since you estimated alpha and beta, yi hat looks like this. So you can plug this into the yi hat. Oops. And by expansion, okay, to expand this, we can write down this one looks like this. Okay. Now consider some property of the residual. Okay. Define I hat as your error. Basically, this is your estimation error. yi is the data, your dependent variable, and yi hat is the estimate of the dependent variable. So it is yi minus alpha hat minus beta hat xi, which is as the residual for the ith observation. And if you add your ith observation, okay, then it looks like this. Like this. Okay, so basically average of your residuals from your regression is basically sum of them is basically 0. Okay. You know, do you remember yi squiggle is the difference between the mean? Essentially, the deviation from the mean of the. To remind you, for some variable, rational variable, squiggle means basically x minus x bar, right? X bar. The deviation from the sample average. So you can transform, basically this one should be equal to this one. And therefore it is 0. And also note that it is the cross product, it is product of the residual and your independent variable, x, explanatory variable. So if you multiply them and add them, then basically this one is same to this one. Again, because we know x squiggle is xi minus xi bar, xi minus x bar, and average of this one is 0, so this is from this one to this one. And we can expand this residual as this one. Okay, so we can write this. And then, since we know the beta looks like this, and this cancels out, so this will become 0. So actually, it is very important. The cross product of your residual and your explanatory variable is 0. Right? In this simple univariate regression, there is two explanatory variables, right? One is x. What is the other? Constant. Right? yi equals alpha plus beta xi. Right? So basically it means alpha multiplied by 1. So 1 is hidden in the explanatory variable. So basically we want to fit y with x and a constant. Right? So cross product of your residual with constant 1 and si is all 0. Right? That is very important property of the regression. Okay, so which means that, okay, and the difference between this cross product of y residual error and y squiggle is actually the difference between your estimate of the y and average y. You can transform this, so it is also 0. So basically we can rewrite equation 10 means it is 0. We can rewrite equation 10, which is this one, and this part is 0, so it is basically sum of this part and this part. Sum of this and this part. So this looks like a Pythagoras theorem, right? You can regard this one as the distance, right? Square the distance of the 2 points. Square the distance of the 2 points. So first part is basically okay. Yeah, anyway. Okay. So basically, the second part is this part is basically yi, and y bar. And then y. So this is two parts, that part from that part. So I had this residual sum of the error. Yeah, something like this. Okay, it looks something like this. So it is total. So square root of this one, right? It is total sum of square errors. Like that. And we usually call this part as residual sum of squares. The residual sum of the squares. So yi minus your estimate of the y, which is your regression residual, right? So this time is residual sum of the square. And then basically goodness of the fit. The most popular measure for goodness of the fit is R square. And so you can R square is TSS over RSS. Actually, sorry. Okay, so it is the not RSS. It is the y minus y I have. So it is the ESS. So this distance is the residual sum of the square. So it is basically 1 minus r square. Look like this. So r square is ESS divided by TSS. So basically, in R square, if you see the homework, then in your homework, it automatically generates R squared, and R squared geometrically mean how well it is your data you are on target, and it is your estimate. And if your model is correct, then the distance between these two should be as close as possible, should be closer, right? The variation you exploit with someone's curve should be similar to TSS. So the larger the RSS becomes, the less actually your regression model becomes based in R curve. So therefore, you want to make this one small and want to make this one as close as possible to this one. And R curve basically measures that. So you can regard the R squared as the, where is it? R squared as the ratio of the two distances in this triangle. And then it is clear that R squared should be always between 0 and 1, right? It is clear from this geometric interpretation. This one should be greater than this one, right? So R squared is always greater than equal to 1. And then our hidden hypothesis is whether R squared is 0 or not, when we can regard R squared. R squared equals 0 means that basically our model is useless, right? Our model doesn't fit anything, so just entire the variation of the data is actually thanks to error. So R squared equal to 0 means our model is totally useless, and R squared 1 means that our model fits the data well. And then the question is, if R squared is somewhere in the middle, how we can judge our model fits data well or not? That's another question. So now consider whether beta is 0 or beta is greater than or equal to 0, and we can show that residual sum of squares. Okay, I will explain later on, but residual sum of squares RSS is basically distributed chi-square distribution with n minus 2 degree of freedom, and EX is as is chi-square distribution to 1 degree of freedom. And it is also easy to show that they are independent of each other. Therefore, by the definition of F distribution, okay, F distribution, okay. This is the definition of F distribution. So therefore, this n minus 2 ESS divided by RSS should be distributed with F distributed degree of freedom 1 and n minus 2. Therefore, since we can calculate those values and we know the distribution, therefore we can test whether our model is basically greater than. We can test whether our model fits data well or not. We can test the hypothesis of whether R squared is 0 or 1. Now, in particular, since R squared looks like this, we can transform this formula like this. Okay, so basically, ratio of R squared divided by 1 minus R squared and we blow by n minus 2, then it's basically distributed at distribution. So I just looking at R squared value, okay, and then you can see whether the model, whether this rejects the hypothesis that R squared is 0 or 1. Right? So given your regression model, so if you take a look at R, then in R there is a multiple R squared in 현장's model. Multiple R squared is basically 0.6%. In 현장's analysis, R squared is 0.6%. 49% actually. And F statistic is 0.186, right? So given this R square looks like this, and we will just plug this R square into this, right, into this, and there's number of the data. And here actually we can find, so instead of 2, we have 4 independent variables, so it should be 4. So n minus 4, actually in 현장 data, what is n? Number of data. What is number of data? Okay. In 현장's data, it is 94 degree of freedom. So 현장's data is, there is 98. Per data is 98. So per sheet use 98 data point, 98 and minus 4. So in 현장's model, it is 94 degree of freedom. So basically 현장's model, it is 94 multiplied by 9 and 1 minor, which is in this example after statistic 0.189, and p-value of this one is 0.9. 0.9, so it is p-value. So which means that actually intuitively this R square looks very low, which is actually very low, and this F statistic is also very low, which means that P statistic P value is almost 90%, which means that we cannot reject the hypothesis that R square is 0. Since we cannot reject hypothesis that our R square is significantly different from 0, therefore we have to reject the model. So basically, F distribution looks like this. F distribution looks like this. It looks like this. Actually, I'm not sure. It depends on degree of freedom. F distribution looks like this. And in 현장's regression, F statistics somewhere here, 0.8. And this area is 90%. 90%, right? Therefore, with 90% of pass probability, F statistic is greater than 0.8. Right? Not F statistic, yeah, 0.18 actually. 0.18. With almost 90% chance. Even if we accept the hypothesis that R square is 0, with 90% of time, the R square value, the F value is likely to be greater than 0.18. Therefore, we have to reject the hypothesis. We have to reject the we cannot reject the hypothesis that R square is 0. Because this thing can happen 90% of the time with the hypothesis that R square is 0. Yeah. Any question? So do you think you can interpret your analysis now? So please do your homework again and review these concepts. And let's go to the next topic. And before so it is univariate regression. It has only one x, right? Two independent variables. One is constant, which is trivial independent variable, and we have only another serious independent variable x. And we natural extension is we want to introduce more x, right? More variable as an independent variable. Okay, then how to do that? Before doing that, actually we have to know some matrix algebra. Okay, so let's go over just minimum linear algebra. Okay. Basically, so this is our regression model. Our regression model basically looks like this. Okay, so consider the model. So basically, we developed our model such that we wanna explain y in terms of the x. Right? We wanna explain y in terms of the x. and we assume linear relationship, okay, and we have n number of independent variables, and we have t large T number of the data points. Okay? We have T observation, and we have n independent variables. So our total data, size of the data is including dependent variable. We have n plus 1 multiplied by T number, T size of the data. Now consider some example. Okay? There are many examples like the Fama-Francis three-factor model. The previous homework is a good example of this one. Yeah. And ordinary least square estimation, OLS. We want to find OLS estimate of the X. Basically, we want to estimate this beta. Right? We want to estimate this beta. Once we estimate this beta, then we know given X, we can conjecture Y. So how can I estimate beta? There are many ways to estimate beta, but the easiest one is OLS relation, ordinary least square relation, and the definition of OLS is this one. Right? So basically, the beta, the OLS beta, meaning the beta, then minimize the sum of the square. And our goal is, of course, to calculate, to find those beta, then minimize this equation, and it is not difficult to find those beta. To find those beta, we have to take differentiation with respect to beta, right? And we have to set to 0. So the first order condition looks like this. Right? So we take derivative with respect to beta and give 2 outside and we have minus, that's 0, so 2a minus goes away. So basically they are first order condition. And how many first order conditions we have? We have n independent variables, so we have n number of, right? We have n number of first order conditions, and we have n number of parameters to estimate. So which means that we can solve this, right? So basically we can solve this. In general, solving for beta 1 hat to beta n hat can be done without matrix algebra, okay? But it's very tedious and messy, right? So, but matrix algebra, it provides a cleaner and more elegant way to handle this kind of problem. So, basic structure and notation. We can rewrite this equation, okay? We can rewrite this equation very succinctly this way. So this is the column vector of our dependent variable, and we have n column vectors of our right independent variable, and of course we have t observation, right? And they are the parameters we want to estimate, and they are error term, some error term, which is the information, which is the variation that our linear regression model can capture. So anyway, since we can rewrite equation 1 in this way, by defining matrices properly, okay, this can be written this way, right? So this is x, this is beta, right? This is epsilon, and this is y. So this is vector, column vector. Y is what? T by n matrix. Beta is n. It is a column vector with length n. Epsilon is the column vector with length t. Where y, x, beta, and epsilon looks like this. And properties. So xti is t and I. Tth column, actually, is ti's element in the tth row and i's column of the x. So if we transpose x, we have n by t matrix. And of course, we do the transpose again, we have original matrix. And diagonal matrix and identity matrix. About diagonal matrix, you know what is diagonal matrix, right? X is diagonal matrix. X is diagonal matrix if this diagonal term is non-zero and off diagonal terms are all zero. And identity matrix is basically square matrix with kind of diagonal matrix with diagonal only one. And this is usual matrix. So we have equal two matrices A, B, and we can define some of the matrix like this way. So you define element by element addition. Note that two matrices can be added only if their dimensions are the same. If dimensions are different, we cannot add, of course. It is high school math. And multiplication, okay. Definition, the way to multiply two matrices exactly. Note that two matrices can be multiplied only if number of columns in the first matrix equal to number of rows in the second matrix. Okay. Also note that in general, BC is CA. And then note that if we take transpose of multiplication AB, it is B prime A prime. Okay. You learned this in high school, right? I repeat. And if I is the identity matrix, in this case, IA equals AI, I. Okay. And if you multiply constant to A, you can multiply constant to A matrix, and it is basically element by element operation. And linear independence. Suppose there are n vectors, x1, x2, so xn. So it is not number, it is a vector, n vector, and define, okay, ci, xi. So basically we want to multiply some constant to each vector, and you can add them all. And it is the summation of ci and xi. Consider n vector, define this to be a linear combination of axes. Where ci is a scalar. Scalar is just constant, it's a number. If the only set ci, c2, cn such that ci, xi is equal to 0 is 0, then it means x are linearly independent. Otherwise, they are linearly dependent. Okay? So basically, it means linear combination of vectors are 0, right? And if setting all equal to 0 is the only way to make this linear combination 0, then they are called linearly dependent. Linearly independent, right? Otherwise they are linearly dependent. So intuitively speaking, it means that they are linearly, those vectors are linearly dependent on each other. If we can express one of the vectors with a linear combination of others. So this is 0. So if or not all C's are 0, the solution for this, the C, to solve this equation is not all 0, then basically we can write such that x1 equals Ci divided by C1 x minus R equal 2 to n, right? You can write it this way. Okay. For example, if the coefficient for the first item is not 0, okay, which means that we can express one of the vectors with linear combination of the others. If we have this kind of relationship, we say those vectors are linearly dependent on each other. So, example, x1, 1, 2, 3, x2, 1, 3, 2, x3, 2, 4, 6, and x4, 3, 8, 7. Then x1, x2 are linearly dependent independent, right? Multiply something here in front of this and multiply something in front of that, and we cannot make it linear combination 0 without setting C1 and C2 0. Or identically speaking, we cannot express x1 or x2 as a multiplication of the others. Right? Whatever constant we multiply over here, we cannot make. So x1 and x2 are linearly independent. On the other hand, x1 and x3 are linearly dependent. Right? And if you compare this and this, simply by multiplying 2 in front of this one, right? Then you can make x3. Right? So they two are linearly dependent on each other. So if you multiply minus 2 over here and multiply 1 over here and add them up, and they are all 0, right? And we can make 0 factor without setting all coefficients 0. Right? So they are linearly dependent. And x1, x2, x4 are linearly dependent again, because x1 multiplied by x1 plus 2x2 minus x4 is all 0. So coefficient is 1, 2, minus 1. So we can make it 0 without setting all coefficient in front of that. And rank, another important concept is rank. And rank is number of independent column vectors in a matrix. For example, okay, X is, now we bind those column vectors. So basically, X is 3 by 4 matrix, right? 3 by 4 matrix from the equation 2. Then rank X is 2, X equal 2, right? Which means that we stack these together to make a column, then there is only 2 independent column vectors. Right? Other 2 can be spanned with linear combination of the other 2. And if all of the columns of matrix are linearly independent, then the matrix, we call the matrix as full rank. Now, invariability. Given the matrix A, and if there exists B such that AB equals I, then we call A is B's, B is A's inverse matrix, or A is B's inverse matrix. Okay? If A is a full rank, then A inverse always exists, and notes that AB inverse is B inverse. And if A and B are both full rank, the column, those vectors are vectors in the matrix are linearly independent of each other, and only square matrices are invertible. And inverse matrix should be A, right? And transpose of inverse is inverse of transpose. In high school, how we can judge a matrix is invertible or followable? How can you know?
B square minus 4H.
Yes.
It's not 0.
Yeah, so basically determinant, right? You could determinant. So basically determinant of the matrix, basically it checks whether a matrix is full rank or not. Basically, they have same meaning. And partition the matrix, okay? Let A and B looks like this. And here, A11, A12, A2, they are all sub-matrix. Okay? They are all sub-matrix. So A and B, okay, looks like this. And if all of the sub-matrices are addition conformable, and then it looks like this. A multiplied by B is looks like this. Now, another important concept is eigenvalues, eigenvector, which was very important in our principal component analysis, right? Consider a square matrix A, okay, square matrix which has the same number of row and column. Consider a square matrix A, and consider all of the solution to ax equals lambda x. So here a is n by n matrix, x is n by 1 vector, lambda is a scalar, x is n by 1 matrix. The value of lambda that satisfy equation C are called eigenvalues. Okay? Eigenvalues of A, and the associated values of x are called eigenvectors. Okay? Do you remember eigenvalues are what? The values of a principal component. Right? In principal component analysis, those eigenvectors, normalized eigenvectors, are called factor loadings. So lambda satisfies 3 are eigenvalues and associated values are eigenvectors, and A has n eigenvectors. So if rank of A is m, which is smaller than n, then n minus m of the eigenvalues will be 0. Okay. And so which means that, okay, if a square matrix has full rank, then it should have equal number of non-zero eigenvalues. And associated eigenvectors will define the particular linear combination of columns of A that equals 0. So what? Which means that if we multiply, suppose we compute the eigenvalues of a given square matrix, and if we multiply eigenvalues, and if it is 0, what does that mean? Suppose we multiply all eigenvalues, and if we consider what does that mean? So for A matrix, it is n by n matrix, and it has eigenvalues are 1, n. And if we multiply them all and it is 0, which means that one of the eigenvalues are 0, right? If some of the eigenvalues are 0, which means that the number of eigenvalues which is 0 is the that is okay, n minus that number is basically rank, right? Rank of the matrix. Anyway, it means that if we multiplication of eigenvalues is 0, it means that at least one of the eigenvalues is 0, which means that the matrix A matrix is not full rank. A matrix is not full rank, which means that it is not invertible. There is no inverse matrix, right? So it is similar to high school math, right? In high school math, if a determinant of the matrix is 0, right, it means the matrix is not invertible, right? So basically, in high school math, basically, in determinant of matrix is mathematically equivalent to the multiplication of the eigenvalues. They are same. So basically, when multiplication of eigenvalues are 0, which means that determinant of the matrix is 0, which means that a matrix is not invertible, which means the matrix is not full rank. Now, positive definiteness. Consider a square matrix A, and A is positive definite if for all x not equal to 0 and x prime ax is greater than 0, and A is positive semi-definite if x is not 0 and x prime ax is greater than equal to 0. Okay? Again, A is called positive semi-definite if x prime ax is strictly positive, or semi-positive definite. Okay, semi-definite if x prime ax is greater than equal to 1. Okay. Strong equality and weak equality. Equivalently, if there exists x such that we can decompose A into the x prime and x, then it is positive semi-definite. And if there is x such that A is x prime x with n equal to m with rank x equals m. Okay, all of the column of x are linearly independent. Then again, A is positive semi-definite. If all of the eigenvalues of A are positive, then A is again called positive semi-definite. And if all of the eigenvalues of A are non-negative, then A is positive semi-definite. They are actually very easy to prove each other, but given that we don't have enough time, and there are other books about it, so I'll skip this proof about it. And A is called negative definite if there is X such that X prime A is strongly strictly less than 0. And A is called negative semi-definite if X prime A is less than or equal to 0. And if we can decompose A as a minus X prime X, then A is negative semi-definite. And if there exists X such that X prime X A is negative of X prime X, and if N is greater than M and rank X is M such that all of the columns of X are linearly independent, then A is called negative definite. And if all of the eigenvalues of A are positive, then A is positive definite, and if all of the eigenvalues of A are non-negative, then A is positive semi-definite. Okay. That is actually yes. And if A is positive definite, then we have always A inverse exists, and A inverse is positive definite as well. And if A is positive semi-definite, then minus A is negative semi or definite. Now let's take an example. Actually, let's skip the example. Okay. And next, some statistics. I think this is very nice PDF. Okay. In this class, all you have to remember is just this one, these 8 items. Okay. And I think you are all familiar with that. If X is distributed with is a normal distribution with mean mu and variance sigma square, and X minus mu divided by sigma, this is called normalization. Right? It is scaling. Okay. We did this operation for principal component relationship, right? And you should be distributed with standard normal. If X is a standard normal distribution, okay, X squared is chi-squared with degree of freedom 1, okay? And suppose we have 2 chi-squared with p degree of square and p degree of freedom and q degree of freedom. And if X and Y are independent of each other, okay, then X plus Y are chi-square distributed with P plus Q. And if X is distributed with standard normal, Y is chi-square distribution with N degree of freedom. And if X and Y are independent and X divided by square root Y divided by N, it is T distribution. And if we have 2 chi-square distribution, and if they are independent of each other, and then if we divide each chi-square with their degree of freedom, then the ratio is F distribution. And for T distribution converges to normal, standard normal distribution if we have very large sample. And another interesting important one is multiplying P to F distribution with P and N degree of freedom, and if N goes to infinity, then it goes to chi-square distribution. Okay. So in this case, right, if Q is infinity, right, if Q goes to infinity in this case, and then multiply P over here, then it should be right. Basically, we don't have to take it out of this part. And trivially, T distribution is basically kind of F distribution with 1 degree of freedom of 1 and N. You all learned this in the 경영 통계, right? You should be familiar. Now we are ready to multivariate regression. Okay. Okay, let's go to our example again. Okay. Now we are ready to consider more complex regression model like this. Okay, so there's one constant and we do n variables and this is linear model. So example can be a consumption, y may be the consumption as a function of income, x can include income, interest rate, wealth, unemployment rate, blah blah blah. Okay? Or maybe we can make y as your salary you are gonna make, earning. What's so funny? Why? Why are you laughing? Okay. If there is something funny, please let me know that. Okay. And earning as a function of schooling, age, wage, gender, etc. And housework as a function of children, gender, spouse income, wage, etc. And something like that. Okay. Then in this case, the interpretation of the beta is straightforward. Beta is basically sensitivity. When change in x occurs, how much y will change? So basically, beta is the slope. You can read the beta is slope of that relationship. And for estimation, okay. Now we can write equation 1 more compactly to this one, such that the very first element of the independent variable as 1, right? The first data, we can get the first data 1, so we can get this one, okay? And assumption, such a linear model will correct the specification. Okay? Of course, our assumption is that first, the relation this should be right. There should be a linear relationship. And two, x is the non-stochastic and linearly independent. So this is very important assumption in this. So in this, x is just data we can observe. So it is non-stochastic. And another important one is x should be linearly independent of each other. Right? Now you know what it means by linearly independent. If they are, some of them are linearly dependent on something else, then basically we can drop them, right? And third, expectation of error term should be 0. That's natural, because if it is not 0, then we can include this non-zero element in the very first argument of the data. And then error term is the variance of error term is square, and the error term of the regression model are independent of each other, not correlated to each other. So cross product is 0, and only when t and s is equal, they are sigma square. Therefore, so maybe it is not that necessary at this point, but therefore epsilon is distributed with some distribution with 0 and sigma square multiplied by identity matrix. Okay. And this last assumption implies that yi's are also independent, right? Independent such that since because we have this relationship, so by plugging this y over here, which means that y should be normal distribution with mean dispersed and variance sigma square, right? And now we can go back to our definition of OLS regression. So in OLS regression, basically OLS regression is like this. And we want to find the beta, right? Estimate beta, then minimize this one, right? And the first of the condition, which is the take derivative of L with respect to beta I and setting equal to 0, then they are first of the condition. For each beta I, and in general, we have n equation and n unknown, so we can solve this. So while in theory we can solve for the n unknown without using matrix algebra, again, doing so is messy and tedious. And instead, actually, we can write first order conditions, okay? First order, basically, it is just expansion of this one, okay? So we can write this part like this. And beta I, we can put this beta I in front of here. And now, since we define y looks like this, and x, beta, and epsilon looks like this, and our regression equation is y equals x beta plus epsilon. So therefore, our first order condition about this one, which can be expressed as this one, right? So this part is basically means x prime y, and this part is x prime xy. Okay, so we have this. So our objective is solve for beta, right? Therefore, to solve for beta, it is very natural. We can simply put this one here, right? Inverse matrix. So basically, this is the solution, right? This is the solution for OLS, right? And how do we know that x prime x exists? How do we know? How do you know that exists? The assumption is the inverse matrix should exist, right? How do you know inverse matrix exists? So how do you know it exists? No, I don't need. You know, I assume that x are the data are, right? X is not linearly independent, right? X is linearly independent, so x prime x also has a full length. So since it has a full length, therefore it is invertible. R. Okay, now let's do some practice. And then let's define y. This y is, let's generate y to random number, so r norm t. Okay. So let's do some practice. Any extra? X is R norm mean 0 and how can I generate random matrix? It's x1 looks like this. Random t, okay, and x2 is another random variable t, and let's assume there are 3. Okay, suppose we have 3 independent variables, and let's say beta. The true beta is like C of 1, 2, 3. Okay, so and let's say error term U equals 10. Okay, no T. So our true regression model would be look like variance. Let's make it bigger. Mean 0 and standard deviation of the 3 like this. So the true model is basically, let's say, define x as the C bind x1, x2, and x3. So it means it bind those vectors to make a matrix. So y equal basically our true model is x multiplied by n3. X. What is matrix algebra? I forgot. So R matrix multi. Matrix multiplication. Okay, it is okay. X. This is matrix multiplication. So I'm right. So our true model is x and beta. And plus u. Okay, so it is our true model. Let's run this. Okay. Okay, so y look like this. Okay, so it is our data. So it is up to now it is a true model, right? True model, and we wanna estimate this relationship. Actually, once. Okay, LM. How about without constant term? Without constant. Help. So our model, our hypothesis model doesn't have a constant term. So, okay, model subset weights NA action mass QR true singular. Okay. 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 Got it. So, okay, our regression model is regression 1, which should be LMY of -1. We want to drop constant term and x. Okay. Let's do this one. Okay. 1, 2, it should be close to 1. Okay, anyway. Okay, so it is our original model. So it is the original. I put -1 in front of it. So I put -1 here because I want to drop constant term. Okay, so if I don't have -1 over here, okay, if I don't have -1 over here, and if I do the regression, okay, so without -1, okay. Okay, without -1, we should be, right? Now we have intercept term, right? But in our original model, actually, I don't want to include intercept term, right? Given this our setting. So I exclude the intercept term here, okay? Now this is the regression model, okay? Regression model with the built-in function of the R, right? This is how you did your homework. And now, since we know, okay, how to do the regression through linear algebra, right? So this is how we do regression with linear algebra, right? So actually we can use this one, okay? So alternatively, okay, in beta 1, alternative way to calculate beta. So actually, let's say beta 1 is the coefficient. So they are the coefficient from the first regression, okay? So let's try. So beta 1 looks like this, okay? Oh, sorry. I wanna put minus 1 over here again. Minus 1 plus. Okay, so this is the first regression, and I want the second regression, okay, using the definition of using the linear algebra we learned. So it looks like, okay, it is x prime x inverse x prime y, right? So we can do this. So x transpose of the x, okay, let me check. X t. Okay, it is a transpose of x. So t transpose of the x and multiplied by x. Okay, and I wanna calculate the inverse of this one, and then in R, how can I write the inverse matrix? Let me check it. R inverse matrix. R inverse matrix. Okay. Inverse matrix, it is solve, okay? Okay, you can use solve only if your matrix is not square. It is square matrix, so it is solve. So what we can do is solve, and then multiply. Now t x multiply y, right? So this is the exactly same as this one, right? X prime x inverse x prime y, okay? And this parallel should be equal to this one. Okay, so let me try. So beta 2, so, and beta 1 was this one. So they are same. Okay? So it doesn't matter whether we so we reach the same answer by using the linear. I think there is another way to calculate this one, which is using solve function. So beta 3, let's say solve. Let's say solve. R solve linear equation. Solving system of linear equations. Solving linear equations, okay? A b equals x with b being a matrix Mn. Solve to work for Mn matrix. Okay. Solve AP. Solve. Help. Solve. So solve is the generic function. So the equation ax equals b for x, where a b is equal to, so I can solve a b. Okay. So another one is basically, okay. So basically we wanna solve this equation, right? This is the first order condition, right? So the solution of this one is of course this one, but I think there is a more efficient routine to calculate this beta instead of using this inverse matrix. So actually let's solve beta over here using this solve function of the R. Okay. Solve function. Let's use this one. So basically, okay, what we wanna is solve AP. So AX equals B. So this should be the B, this should be the A, right? So A is A is this part, okay, and B is this part. Let's see whether it generates exactly the same answer. So it is the direct solution from first order condition. Okay, so the 3, right? It is the same answer. So let's combine together C bind. So there are 1, there are 2, and there are 3. So they should be all same. Okay, they are all same. Okay. Again, the first method is just doing the regression function in R. Okay. And the second method is linear algebra. In the lecture, the third one is solving first order condition directly. And they should all be the same answer. Okay, any question? Now, do you think you can do the homework now? In your homework, right? In your homework, it is very simple. So the first item was just the market factor, right? And the second one is HML. Third factor is SMB, right? So all you need was this one. -1, you should have -1, and MKF plus HML plus SMB, right? It should be your homework. Can I see your homework? Did you put -1? Oh, you have interceptor. That is fine, okay? Actually, here intercept is very significant, so please drop intercept. Actually, in constructing factor model, actually we have to drop the intercept term, right? But actually, when we want to develop trading strategy, we often include intercept term over here, like 현정 did. Because in this way, we can basically estimate alpha, right? Alpha of the A stop or S return, which is the excess return that existing factor model cannot explain. So that can be very useful information for asset allocation, basically. But anyway, in your homework, we are not, we don't want, it is not our goal to develop trading strategy. Instead, we want to estimate factor model, and then we want to test how individual asset return matches factor returns. How factor model, factor model can explain the individual assets return, that was our goal. Therefore, we want to drop the intercept term. So please. Any question? Okay, let's take a break. And again, as I said, we will have a guest speaker from 2:30. Okay, so you can leave now. And the guest speaker will be done in Korean. Thank you.